Elon Musk has a new goal. And to be honest, it's just staggering. The plan is to bring 1 terawatt of compute online. So let's break this down. What in the world does a terawatt of compute even mean? Why does it matter? And what kind of insane challenges are standing in the way?
1 terawatt. Seriously, just let that number hang in the air for a moment. What does a number that big actually look like in the real world?
Well, it means Musk is talking about building a computing system that eats up the same amount of power as the entire US electrical grid. That is a mind-boggling, almost incomprehensible amount of energy, all pointed at one single thing: artificial intelligence.
So why? Why on earth would you build something on that kind of planetary scale? The vision, it turns out, isn't really just about building bigger computers. It's about completely reshaping our economy and kicking off a new era of abundance. Here's the core idea. If you have this much compute, AI could basically create an almost unlimited supply of both brainpower and physical labor, and do it for super, super cheap. That would drive down the price of, well, pretty much everything. And we all know, when things get cheaper, human demand, which is practically infinite, just goes through the roof. Okay, but to actually build that future, you've got to get the tech details right. And when we talk about AI compute, it really all boils down to two key ideas: training and inference. First, let's talk about training. This is the really heavy lifting. You can think of it like sending an AI to college for a PhD. You are feeding these supercomputers just mountains of data. We're talking millions of books worth to create that digital brain, that AI model. It's an incredibly power-hungry process. And then you've got inference. This is when all that hard work pays off. This is the AI actually doing useful things. Answering your questions, spotting a cat in a photo, or driving a car. And the key thing here is it takes way less power for each task than the training did. I love this analogy for it. Training is like spending months just grinding away, learning a really complex piano piece. Inference is sitting down and just effortlessly playing that piece whenever you want. Recall is always easier than learning.
And the demand for that learning phase for training compute has just gone completely vertical. As you can see here, before 2010, the amount of compute being used was doubling roughly every 2 years. That's fast. But since the deep learning era really kicked off, it's been doubling every 6 months. That is an exponential curve that is just off the charts.
So the ambition is huge, the demand is definitely real, but this brings us to our first giant roadblock: the great chip bottleneck. If you want to build a terawatt of compute, you're going to need a practically bottomless supply of the most advanced computer chips on the entire planet. And the way you solve that is, well, you don't do just one thing. You've got this 4-pronged strategy. First, you buy every single high-end chip you can get your hands on from NVIDIA. Second, you rent massive server farms in the cloud from partners like Oracle. And then, the big one, you start designing your own custom chips. First with TSMC, and now with Samsung for the next-gen stuff. But this whole strategy didn't just appear out of nowhere. It's actually the result of a massive, and I mean massive, strategic pivot away from a super hyped project inside Tesla that you've probably heard of, called Dojo. So Dojo was this incredibly ambitious plan. Tesla was going to build the world's most advanced training supercomputer completely from the ground up. It was announced back in 2019, huge fanfare, but now, in 2025, the original project, it's been canceled. So what happened? Well, Musk himself called the original Dojo design an evolutionary dead end. Now, does that mean it was a total failure? Not exactly. It's more like the problem they were trying to solve changed, so the strategy had to change with it. And here it is. This is the core reason everything changed. Tesla did the math and realized that while training is important, it's only about 5% of what they'll need in the long run. The huge, overwhelming majority, a whopping 95%, is going to be inference, happening inside millions of cars and robots out there in the real world. This huge realization led to a totally new strategy they call convergence. Instead of building one crazy expensive specialized chip just for training, the new goal is to build one single chip that is excellent for inference and, just pretty good for training. That one chip can then be used everywhere, in cars, in robots, in data centers. It's way more efficient.
But okay, let's say they totally solve the chip problem. You'd think you're in the clear, right? Wrong. It's like beating a boss in a video game, only to find out the next one is 10 times bigger. You go from the micro challenge of chip precision to the macro challenge of pure physical infrastructure and power. It's a constant game of whack-a-mole.
This table just lays out the difference perfectly. The chip bottleneck is a problem of precision. You're dealing with companies like NVIDIA who have these fat 50% profit margins because what they do is incredibly difficult. But the power bottleneck, that is a problem of pure scale. The parts, like solar panels, have tiny 5% margins. The hard part isn't making one perfect thing, it's the unbelievable physical mass of what you have to build.
Let's try to put this into perspective so we can really feel it. Let's say you manage to get 2 million AI chips for your new data center. The physical weight of those chips is about 40 tons. That's a lot for sure, but manageable. But now, get this. The batteries you would need just to support the power grid for those chips, that could weigh 40,000 tons. That's 1,000 times more massive. And that's not even counting the solar panels or the rest of the equipment. That is the difference between a precision problem and a scale problem.
So, if there's one thing to take away from all this, it's this. Scaling to a terawatt isn't about solving one bottleneck and then you're done. No way. It's about mastering this constantly shifting dance between the nanoscale world of silicon precision and the gigascale world of steel, concrete, and copper. And this whole monumental engineering challenge, it all comes back to that first big idea, creating abundance, which kind of leaves us with one final powerful question. If this vision actually succeeds, if the cost of intelligence and energy basically drops to zero, what's the first impossible problem that you would want to solve?